All right, so let's practice beam selection. We have a simply supported beam and it needs to support a total of 108 kips that's applied uniformly over a 10-foot span. So here's our 10-foot span. Uniform load totals to 108 kips. We need to choose the just any old acceptable rectangular hollow structural section. We want to find the cheapest. And when I say cheapest, I always mean lightest. Usually, there doesn't list prices of steel in the book. That fluctuates, but you can often assume that if it's going to be lighter weight, then it's going to be less steel, less expensive. The cheapest rectangular hollow structural section, the cheapest W section, assuming there's no bracing. Now remember that bracing does not refer, I've told you that this is simply supported. That tells you nothing about whether there's bracing or not. Bracing means is there into and out of the page supports. And they can be very lightweight. They can be just tension wires like on either side, as it showed in the video, at a few different points, maybe just at the midpoint, maybe at 3 different points. You can have continuous bracing, like if this is part of a building or if this is the bed of a trailer or something like that, then the compression flange of if it was an I-beam W section, if that is attached to frequently, like plates of steel or boards or something like that, that prevents the steel W section from bending into and out of the page. So if I look at it from the top, I'm looking at it from the top. Anything that prevents it from deflecting laterally and twisting along its axis is going to be considered bracing. And so first we're going to say there's no bracing. This is just a simply supported beam and there's no bracing. There's nothing stopping it from bowing out into and out of the page. That is nothing except for at the ends. We always assume that the simple supports also provide bracing, but there can be additional bracing in addition to the simple supports. And the second case is when there's continuous bracing, and that means that there's like, say, a plate of steel all along the top of this that is supported. So one way that you can achieve that, let's just draw a picture. You've got multiple I-beams, W sections from the top. We're looking from the top now. And you've got several of them. And then over the top of all of them, maybe you'll have wood or concrete slab or steel slab, plate, something like that. It can be thin, but it's over all of them. And it kind of holds them together and they kind of stabilize each other against deflections. All right, so let's find any old acceptable rectangular hollow structural section. Now we choose sections based on their moment carrying capacity. For a hollow structural section, we want to find something for which the moment, the plastic moment, or let's use the nominal moment over the omega of bending, is greater than or equal to the maximum moment that we experience inside our beam. So these are tabulated for hollow structural sections. This is something we're going to have to calculate based on our load of 108 kips. So remembering from the beginning of the preparation, we said that in Chapter 3, Table 3-23, there is a shear moments and deflections table. Let's find that. And so I've given the simplest loading condition that we can probably have, which is the uniformly distributed load. But we've already talked about more complicated cases, right? We've used the Shigley book and the equivalent table in the Shigley book, I think it's A9, that shows us how we can use superposition to break down more complicated loads into these simple loads, and we can find the maximum moment that is experienced anywhere in the beam. For this case, it's really simple. It's a uniformly distributed load. The maximum moment occurs at the center, and it is lowercase w times L squared over 8, where the total uniform load is lowercase w times L. So let's write those things down. I've already written the first one. Lowercase w times L is 108. So we want to find out what lowercase w is. That's capital W over the length is 108 divided by 10 feet. That is 10.8 kips per foot. And then the maximum moment, M max, which happens to occur at the center of the beam, is lowercase w L squared over 8. I suppose that's equal to capital W times L over 8. And that is 135 kip feet. So this is 135 kip feet. We want to find any old acceptable rectangular hollow structural section that supports that. We need to find one for which the available flexural strength, this quantity here, which is for hollow structural sections, the nominal moment, available moment is equal to the MP, the fully plastic moment, divided by our factor of safety, and we're using ASD, available strength design safety factor. This is 1.67. We can look it up in the table. So we're going to design this so that it's bending about the strong axis. Okay, this one works, right? Hollow structural section 20 by 12 by 5/8. Our available flexural strength is 574 kip feet. That is greater than 135. So almost anything in this page is going to work. You would not be able to use HSS 14 by 4 by 3/8 though, right? Because that has an available flexural strength of only 119 kip feet. So that's not going to be enough. So that part was easy. You just look up in the green column for ASD any section that has an available flexural strength that's greater than what you require. But the cheapest rectangular hollow structural section, how do you find that? Well, that's a little tougher. Unfortunately, we said cheapest, the costs aren't listed here, and the weights are not listed here. And by weight, I mean the weight per unit length, the weight per foot. So it's kind of tough. You'd have to kind of look for a small section. Typically, it's laid out from big, deep sections, and these the second numbers correspond with their width, right? And the thickness is here. So you'd probably want to look further down in the table. You'd probably want to find something with the thinnest walls and the smallest width, probably. Smaller width is probably better. Thin walls, small width, really deep is probably what you want. But it's kind of hard to tell. This table is not the best place to choose the least expensive hollow structural section. It might be a good place to confirm your pick, but I think that the best way to choose the cheapest hollow structural section is actually that table from 1. What we want to do is we want to say, all right, hollow structural section is made out of material with a yield strength Fy equals 50. So we know Fy equals 50. So another way that we can do this, we know that Mn over omega b, Mn is equal to our fully plastic moment. We just learned about that. That's equal to the yield strength times the plastic section modulus z. So if we divide both sides by omega, we want to choose that so that that is greater than the maximum moment that you experience in the beam. And we know what this is. We know what our safety factor is, 1.67. We are going to solve for z. So z needs to be greater than or equal to our M max times our safety factor divided by our yield strength. So let's calculate what z needs to be greater than. This is equal to 135 kip feet times 1.67 divided by 50 KSI. Now we have to be careful here. This here is in kip feet. This is dimensionless. This is in kips per inches squared, or KSI. So we're going to have to take this and we're probably going to multiply it by 12, right, to change it from kip feet to kip inches. We're looking for a z that is greater than 54.1 inches cubed. And then we need to find the lightest beam that has that z. So we look in part 1. Table 1-11 has our rectangular hollow structural section. So I like to start at the back. So let's flip a few pages over. All right, so we're not seeing anywhere near on this page, for instance. We've gone a little bit too far, and that's okay. all of the z's that we see here are, much less than what we need. 13.4, 12, 21.9. We want to find a page where none of them are close to what we need. Right, we need 51.4. So those are not nearly so. And so then we're starting kind of towards the back, and then we're going to look for larger sections. All right, so now we're at a page that has a little bit larger sections. Still not quite what we need. So then we're going to get to, let's see, it looks like this one's getting close. HSS 9 by 7 by 5 eighths, 48.3, still not what we need. Okay, now we're kind of at a page where the sections are starting to get big enough. And again, we're looking for 54.1. So HSS 10 by 6 by 5 eighths, this one's not going to work. Some of these sections are going to work. HSS 10 by 8 by 5 eighths is going to work. This is a candidate, and it has a weight, nominal weight in pounds per feet of 59.32. So I'm going to mark that down. I'm going to be really careful, and I'm going to actually write it down. When you get the hang of this, you don't have to write everything down. But actually, on your homeworks, please do write everything down. So I'm going to make a little table, and what I'm going to say is the z that I need is equal to 54.1. That's what I need. So I need it to be greater than that. And then what is the weight? Little lowercase w, pounds per foot. And then the shape. Okay, so we found that 10 by 8 by 5 eighths, that had a z, the last column. I'm blowing it up so that you can see a little bit better. I'm sorry that we can't get everything on the page at the same time. Capital Z for this section, 10 by 8 by 5 eighths, was 62.2. And it had a weight, the second column, 67.82. This is in inches to the third. This is in pounds per foot. So then we keep on looking up. We find the next one for 54.1. All right, 54.1. This one is bigger. This one's 55.5. Sorry, that's bigger than 54.1. So 55.5. The weight of that section is 59.32. And it is a 12 by 4 by 5 eighths. Okay, so why is it lighter? Well, it's taller, it's deeper. It's lighter because it's skinnier. It's not as wide, and the walls have the same thickness. We're going to want to try to find something that is, probably pretty tall and skinny and has really thin walls, because we're interested, all we said is that we need to be able to handle a bending moment about this axis. If it's really tall, it's going to have a high moment of inertia. It's going to have a high plastic section modulus for its weight. So we keep looking up the table. All right, this one, 57.4. What's its weight? 55.6. Now this one is higher up on the table, but it has a higher weight than the best that we currently have. 55.66 is higher than 55.5. So we don't have to even write it down. That's not even a candidate. We don't have to write that down. 68.8. Well, that's 67.82. That's heavier than one that we already found that would meet our criteria. So we only really need to write down the ones that are lighter and still meet the criteria. So let's go back a page. Looks like this section, 68.1, that has a weight of 62.46. That's not going to work for us. 61.1, 53. Ah, there we go. It looks like HSS 12 by 10 by 3 eighths. This one has a Z of 61.1, and it has a weight of 53 pounds per foot. And that is a 12 by 10 by 3 eighths. Now look, even though it was much wider, it's way skinnier. So the wall, sorry, it's wider, but it's smaller wall thickness. So it's going to have it's going to be a more efficient shape for us. And by efficient, in this case, I mean moment carrying capacity per unit weight. So maybe efficient is not the best word. Let's keep on looking up the table. 61.1. where we were. Let's keep going up. Here's 61, 55.66. No, that's not what we want. 57.3, that's okay. 47.9, okay. 57.3, the weight is smaller than what our best one is so far, 47.9, and that comes out of an HSS 14 by 6 by 3/8. We don't have to look at the rest of this shape. The thicker ones are always going to be heavier, so we don't have to look at that. We just need to look up the table, the next shape, 64.6. The weight is 48.86. That's not better than we've seen. So we can ignore the rest of this shape. 47.9, that's the same as we already have, so I think I can ignore that. Oh, 39.43 for a Z of 56.4. 39.43 is the weight. And that is a HSS 16 by 8 by 1/4. Again, thinner is better. And it looks like, let's see, is that our best? We could go to the 59.4. This one, so this doesn't work, right? That's a heavier weight. This one satisfies our criteria. Z is greater than 54.1, but its weight is the same as we currently have. Same sort of thing here, 61.5, 39.43 is the weight. And then above this, we only have heavier sections, right? We can stop when we get to all the sections that are heavier. So maybe actually the best one, I should probably write down HSS 20 by 4 by 1/4. This has a Z of 61.5, which is actually higher than this one. That's okay, because it has the same weight, 39.43. 39.43 here. This is a 20 by 4 by 1/4. And I don't know, in between there, we might want to put this shape, 18 by 6 by 1/4. These all have the same weight, but they have different Z's. I'm going to choose the one probably with the highest Z, assuming that these three sections, because they weigh the same, are going to be the same cost. Now, what you might actually want to do is, if you want the cheapest one, not necessarily the lightest one, is you look up those three materials or those three different shapes, and you find out which one you can get for the least money. So this is going to be our selection. This is going to be our cheapest, actually any one of those three. I'm going to pick this one. That would be a good answer. It's going to have greater Z than you need, and it's going to have the lowest cost. Now, why did we have to start at the far back of the table and keep going up? I mean, you can probably get a pretty good guess based on finding, if you can find maybe the deepest section and the smallest thickness that just barely goes over the Z that you need, that's probably going to have the lowest weight. But the only way that you can really be sure is if you've checked all the other sections that can meet your Z requirement, right? It might be possible that there's a little bit thicker section that weighs less than this one because it's so much less wide, for instance. So you can't be sure unless you go through the procedure that we just did. Now, usually it doesn't take so many steps. I picked an example that required a lot of steps just to show the process several times of going up the table. I also picked an example that showed that, hey, there were 3 different sections that all met our requirement but had the same weight. So I chose a particularly complicated one. It usually doesn't take so long. You kind of go towards the back of the table and you look your way up. You start with the first section you find that has a Z greater than what you need. You write down its weight and you keep on going up the table looking for Z's that also meet your requirement and have lighter weight than the last one that you wrote down until you get to sections. You stop whenever you find that, hey, there's nothing lighter for the rest of the way. Now, before you declare victory, what we've done so far is we've found the lightest section, so hopefully the cheapest section, with a plastic section modulus that's greater than we need. And this is appropriate under the assumption that the moment carrying capacity is proportional to the section modulus, that the nominal moment divided by the safety factor, the available flexural strength, is equal to Fy times Z over our safety factor, right? So this equation is always true. That's how the plastic moment is defined. The fully plastic moment is simply the product of the yield strength and the plastic section modulus. But it's not always true that the nominal flexural strength is equal to the plastic moment. Other things can happen. Just like you saw with beams in the video, long beams can experience lateral torsional buckling. Very thin sections of tubes, the walls can crumple. They can experience what local buckling is the technical term. It's not buckling where it bows out of the plane, although that can happen with extremely long sections that are very tall, but it's not something you typically need to worry about. But what can happen is these paper-thin walls, relative to how tall they are can buckle locally. And I'll show you some videos that you can see that. So what you should do is go back and double check your answers. Take a look through this table and look up the strengths. Ultimately, what we were after, we went this roundabout process. We were trying to get something that can handle more than 135 kip feet, right? So we went ahead and we found what Z would be so that we could find the lightest section with that Z, because in this table 3-12, it does list the available flexural strength, Mn over sigma, omega b, which is exactly what we want, but it doesn't list weights. So we went to the other table because it had weights, but we need to check our work because it's not necessarily true that the nominal moment is equal to the fully plastic moment. The available flexural strength might not be equal to the plastic moment divided by the safety factor. So let's check. 20 by 4 by 1/4 is right here, and indeed, it has an Mn over omega b of 141 kip feet. And so we are okay. Now, had we chosen the 16 by 8 by 1/4, actually, we need 135 kip feet. It's a good thing we kept going, right? Because even though these had the same, or they both exceeded the Z we needed, and they had the same weight, we said we could have stopped here, but we kept on going because we said, oh, well, we can get the same weight, but a higher Z with our 20 by 4 by 1/4, right? But had we stopped here at 16 by 8 by 1/4, that has an available flexural strength of only 124 kip feet, which is less than 135 kip feet. So fortunately, we don't have to go back in our table. What you would do, let's say that this section had not had a available flexural strength that was great enough. We went back in the table and it turned out that the nominal flexural strength is not the same as the fully plastic moment. There could be some local buckling that occurs. If that had happened, what we do is go back through our table and keep on looking backwards until we find one that does check out. And fortunately, the very last one in our table, the lightest one with the highest Z, turned out to have the available flexural strength that we need, 141.